Hello. So in exercise 7, we were asked to find the solution to the time-dependent Schrödinger equation. Okay, and so first of all, we're going to start off with a state vector psi, okay, as I said before. So let's say we already know the eigenvalues and the eigenvectors of our Hamiltonian, okay, Ej. Okay, so since the state vector varies with time, okay, one of these has to vary with time, okay? Ej can't vary with time because it's a constant, okay, it's an eigenvector, so therefore alpha j has to vary with time. So therefore we can write psi of t, okay, it's equal to Ej alpha jt. Okay, right, so if we feed this equation into the time-dependent Schrödinger equation, okay, I'll remind you what it is. We have the partial derivative, okay, and it's equal to minus I h bar h times psi. That is the time-dependent Schrödinger equation. So if you just feed this equation into this one, okay, so we need to, first of all, this side, we need to take the partial derivative of our state vector with respect to time. So therefore, we get the sum of j. Take the derivative of alpha j. We're going to get alpha dot j. Okay, that varies with time. Ej, and this is going to equal minus I over h bar h times our state vector j. Okay. Ej. Okay, right, so that's very simple. Right, so the next step is to use the fact of your Hamiltonian acting on Ej is going to equal our eigenvalue Ej times the same eigenvector. Okay, this is the time-independent Schrödinger equation. Okay, so if we use the fact that Hej is equal to Ej times our eigenvector, we can rewrite this equation. Okay, so if we use this equation here, we therefore get the sum of j alpha dot j. Okay, alright, and this is going to equal minus I over h bar times the sum of j Ej times alpha j t, and then we multiply that by Ej. Okay, so we can get rid of the Hamiltonian. Right. Okay, so we can rearrange this equation, alright? If we regroup it, we can therefore get the sum of j, okay? We put that in brackets, we have alpha dot j t, okay, and then we can add I over h bar, just bring it to the other side, times Ej times alpha j, and then obviously it varies with time, and all that's multiplied by our eigenvector, and that's going to equal 0. Okay, so the final step should be easy to see. Okay, if a sum of basis vectors equals 0, every coefficient must be 0. Hence, for each eigenvalue, Ej and alpha jt must satisfy the simple differential equation. Okay, the differential equation is therefore going to equal, just using the term in the brackets, we therefore have a differential equation of rate of change of alpha jt, okay, this is going to equal minus I over h bar and then we multiply that by Ej times alpha jt. Okay, that is our differential equation. Okay, this is of course the similar differential equation for an exponential function of time. Okay, in this case with an imaginary exponent. So we can very easily work out the solution to this differential equation. Okay, that's what we're going to do now. So let's bring this down. There we go. So it's a very simple differential equation. I'll write it out once more. So we had the rate of change of alpha jt, okay, and that was equal to minus I h bar Ej times alpha jt. Okay, so the solution, alright, so it takes the general form, okay, you may have seen this. It takes the very general form y equals c e to the k t, okay, where c is our initial value. Okay, in this case, c would be alpha naught, alpha j naught, okay, at its initial time. Okay, so this is very easy to solve. All we need to do is bring the dt on this side, okay, and we would then integrate, okay. Alright, and of course we bring the alpha jt on this side. So therefore we're going to get the integral, okay. So bring alpha jt onto this side, we're going to get 1 over alpha jt, okay, multiplied by d alpha jt. Okay, and this is just going to equal the integral of minus I of h bar Ej alpha j, oh sorry, not alpha j, we brought that onto the side, multiplied by dt, that's right. Okay, so all we did is bring this term over to this side, okay, which is here, and then we simply multiply both sides by dt and bring it onto this side. I'm going to integrate. Okay, so this is very easy. The integral of 1 over alpha jt with respect to alpha jt is of course the natural log of alpha jt. So it's going to equal the natural log of the modulus of alpha jt. Okay, and this of course is just a constant, so it's going to equal minus I over h bar Ej, and we multiply that by t. Alright, very good. So we can undo the natural log by raising it to the power of the base, which in this case is e. So therefore we get alpha jt. Alright, oh, we need to add our constant of integration, of course. Okay, this is going to equal e to the minus I over h bar Ej t, okay, and then we add c. Alright, so we can therefore rewrite this as alpha jt, okay, is equal to e to the minus I over h bar Ej t, and of course we can add, sorry, we're going to multiply, that's right, and we multiply it by e to the c. Does that make sense? Okay, so what is e to the c? E to the c is just another constant. Okay, so we can rewrite e to the c as just c, okay, in this form we had here. Alright, so therefore we can write alpha jt as equaling, we could just put c for now, c times e to the minus I over h bar alpha jt. What is c? Remember we said c was alpha j naught, our initial value. So therefore the solution to the differential equation is alpha jt, okay, and that's equal to alpha j naught times e to the minus I over h bar ejt. Okay, so that is the solution. So now we have the solution, we can carry on with our state vectors. Okay. Right, so the solution just tells us how AJ changes with time. Okay, it is quite general and not restricted to spins, provided that the Hamiltonian does not explicitly depend on time. Okay, so as we know, alpha j naught, very quickly, okay, as we saw in the differential, the solution to the differential equation, alpha j naught, okay, it's a very simple fact, is equal to the inner product. Okay, of course it's psi naught because we have alpha j naught. It just equals the inner product of the eigenvectors and our state vector. Okay, so now let's put the whole thing together and write the full solution to the time-dependent Schrödinger equation. Okay, so we're going to get psi t, okay, is equal to alpha j, sorry, what am I saying? Sum of j times alpha j naught. Okay, and we multiply that by e to the minus I over h bar e j t, and we multiply that by e j. Okay, so if you remember, this simply becomes, this is solution to the differential equation. As you remember, before we wrote this, okay, alpha jt ej. Okay, so all we're doing is simply substituting alpha j naught e to the minus I of h bar ejt for ejt, as we saw in the solution to the differential equation. Okay, that's all we're doing. Alright, and we can clean this up just by using our equation up here. So overall, we're going to get that the psi, so our state vector that depends on time, is going to equal the sum of j ej psi naught. Okay, I don't think I can put this all in. Just try e to the minus I of h bar ejt, and of course we multiply that by ej. Yes, alright. Okay, so aj naught in this equation, we just put ej psi naught as we had here. Okay, just take a moment to sink that in. And finally, we can write this in a more elegant form. And here we have the solution to the Schrödinger equation. Psi of t is equal to the sum of j ej, okay, psi naught. Alright, and then we multiply that by e to the minus I over h bar ejt. Alright, and there